going to have our first video regarding implicit differentiation. So, what is implicit differentiation? Let's start with that. Let's start with the word implicit. Okay, on the screen here, you see we have ourselves a circle. And back in geometry class, you learned the equation of a circle, which is centered at the origin, like this one, was x squared plus y squared equals r squared. Now, this circle, centered at the origin, we can see also goes through the point over 5 up 0, so that is 5 units away, which means the radius is 5. So this particular circle is x squared plus y squared equals 5 squared, and we all know that 5 squared is 25. Okay, so this right here is the equation of this circle right there. All right, now, this circle, would you agree, goes through a whole bunch of points. Let's say it goes through that point as well. We're going to call that point over 4 units and up 3 units. All right, over 4, up 3. Okay, now I know that this point goes is on the circle because if x is 4 and y is 3, we have 4 squared, which is 16, plus 3 squared, which is 9. 16 plus 9 equals 25, so the circle definitely goes through that point. Okay, now, since we have this point, we can draw a line which is tangent to the circle at that point, as I've just done. Okay, so we have ourselves a tangent line, and this tangent line will have some kind of slope. Well, wait a minute now, we're looking for the slope of the tangent to a curve at a point, which we know from the song is the derivative. So we can take the derivative of this circle. Okay, well, that means we can take the derivative of this equation because this equation represents the circle. Now, what's different about this equation compared to all of the other equations we've been deriving so far? Exactly. Everything so far has had y on one side and x on the other. All right, that's known as an explicitly defined function. When something is explicitly defined in mathematics, one variable is on the left and the other variable is on the right. When both variables are on the same side, like what we have here, that is known as an implicitly defined curve. Now, we do need to say this is not a function. All right, we know the circle is not a function because it fails the vertical line test. Okay, so we have ourselves a relation here, or a curve, but we do not have a function. Nevertheless, we can still derive it because we can get a slope of a tangent to a curve at a point. So let's derive it. How do we derive it? Through the process known as implicit differentiation. And I've got the steps here underneath the circle. So the first step is that we're going to derive each term. Okay, no big deal. We have 1, 2, 3 terms, and we're going to derive all of them. Okay, we're going to derive the x terms as usual. Well, let's look at our first term. It's x squared. What would be the derivative of x squared? Exactly, it would be 2x. So let's put that down. We have 2x. Okay, now the third step, I'm going to scroll up here a little bit, is that we're going to derive the y terms like the x terms. Okay, but we have to multiply by dy dx. And here's the deal. We can think of y squared as like a chain rule going on here. Okay, we don't have x squared. X squared goes to 2x, but we have y squared. We're finding the derivative with respect to x, which is why we have dx down here in the denominator. Okay, so we're going to derive a y term with respect to x. What does that mean? Well, it means we can treat a y term like an x term. And if x squared derives to 2x, then y squared derives to 2y. But because this is not an x term, we do have to take that into account. And we do so with the chain rule, and the chain rule says we need to derive by the we have to multiply by the derivative of the inner function. Well, the inner function is y, and the derivative of y with respect to x is literally dy dx. So we need a dy dx in our answer. Now, you may think that makes things complicated, but in fact, it works out well for us because dy dx, remember, is just another notation for the derivative. So therefore, we've now got our derivative notation into our equation, which is good because our goal, let me get this down here, our goal is to find dy dx. Okay, well, here's our dy dx. Except we're not done deriving each term yet. So let's go to the next one. The next term is 25. What's the derivative of 25? Yes, it's 0. Okay. So now that we've found the derivative of each term, and we've derived the x terms as usual, and we've derived the y terms like the x terms, we now go to step 4, which is that we need to isolate dy dx. We need to get this dy dx all by itself. Here's where your algebra skills come into play. We got to get the 2x over to the other side. How should we do that? Yep, let's subtract 2x from both sides, here and there. Okay, that gives us 2y dy dx is equal to negative 2x. Now, to get dy dx all by itself, we divide by 2y. Right, in doing so, dy dx is equal to, everybody okay if we cross out the 2's here? So we have the opposite of x over y. And that's our answer. That's our derivative. This equation right here, dy dx is equal to the opposite of x over y. This opposite of x over y gives us our rate of change. It gives us our derivative. It defines our derivative for any point on the circle. Let's go back to the point we were interested before. Let me get up here. Here we go. 4, 3. X is 4, y is 3. So if we were to plug 4, 3 in here, all right, we plug in 4 for x, we plug in 3 for y. All right, that, remember, the derivative is the slope of the tangent line. Would you agree that this slope could be negative 4/3? Does this go down 4 and over 3? It certainly seems like it. We obviously don't have graph paper to verify it, but there's definitely a negative slope on this line, and in fact it is negative 4/3. So implicit differentiation is a way for us to find the derivative of some kind of equation which has x and y on the same side. All right, back in a moment with another example.